Motion of conductor in magnetic field. You have a conductor and that's allowed to move in magnetic field as shown over here. You see the magnetic field is given by letter B. Velocity of the conductor is V and length of the conductor is here L. Whenever the conductor moves in a magnetic field, the induced voltage is developed in it given by the relation B cross B dot L, L, this way. If you consider all three, that is velocity, magnetic field and length of the conductor, all perpendicular, in that case it's going to be V, B, L. Now, you are moving the conductor, voltage was automatically induced in it. Suppose you have this conductor connected with a resistance forming a circuit. This conductor may also have some internal resistance. In that case, the total resistance of the circuit is going to be R plus R. And the EMF that was induced because of the motion of the conductor is E. So, current that way will be equal to E upon R naught. In moving this conductor, obviously some energy, some power will be consumed that could be given by relation I square R naught. And this will be equal to E square R naught square. This will get cancelled. That is given over here. You put the value of this E VBL, you will find the power consumed in the process of moving the conductor. You see, important thing here is that when you say EMF was induced, we normally don't use the term, don't utter the term voltage. We normally always say that whenever the conductor moves in magnetic field, EMF is induced. And EMF always gives an idea of cell. That means when this was moved, it converted itself like a cell. What kind of cell? For that, you need the direction of current. Inside the cell, you know, the current always flows. You might remember the current flows from positive terminal of the cell, but that's about outside. Inside the cell, the current always flows from minus to plus. And here we say that this conductor, when moved in magnetic field, is now behaving like a cell in which the current will be produced. You just apply this law, right hand, this Fleming's right hand rule, field, current, motion. Here the field is normally inward, see, normally inward, and this represents the motion of conductor which is towards right. So, I have shown here the index finger in the direction of field, the thumb in the direction of motion of conductor, middle finger will represent the direction of current. That means we have concluded that in this conductor the current is going to flow this way. This is the direction of current, and inside the cell the current will always flow from minus to plus. So, obviously a cell, a small cell has developed over here. That's what I have shown over here. Now, whenever the conductor will move in the field, induced voltage will be developed. You see, any surface vehicle moving on the ground, there is one axle that is horizontal. It's going to intersect the vertical component of Earth's field. When a player is running north-south, horizontal component will never be intersected like this, you see. But if the same player is running east-west, this horizontal component will always be intersected. Suppose aeroplane is in north-south direction, it is ascending or descending. In that case, the axle would be east-west and this will always intersect the horizontal component of Earth's field. You see, there is one interesting question. This will always remind, the very popular couple of our film industry, Amitabh Bachchan and Jaya Bachchan. Suppose they are running in the park with the same speed. Now, it must be a very clear picture in your mind that the voltage induced in the body of Amitabh Bachchan is going to be greater. Why? Because the formula for induced voltage involves the length, and length, obviously, length or the height of the person involved here. Length or height is greater for Amitabh Bachchan, that's why the voltage induced would be greater in him. And finally, we must know here why this current is clockwise and why this is produced anti-clockwise. The inward field is getting decreased. You see, the coil is pulled in a manner that inward field is getting decreased. Then we want a current that produces inward field, and that could be only clockwise current. In this case, the inward field is getting increased gradually. So, we want another current that is going to reduce this inward field. That is possible by producing outward field, which could be produced only by anti-clockwise current. Then field induction. You see, a stationary charge always produces electric field that is conservative, and in this conservative field the work done is independent of the path. When there is a changing magnetic field, it is likely to produce induced electric field which is non-conservative in nature, and in such types of field the work done is always dependent on the path. Electric lines of force are closed curve and potential cannot be defined for non-conservative field. Here the induced EMF is not confined to a point or loop, rather it is for the complete circuit or whole circuit. In the two field, conservative and non-conservative, you could have the differentiation by learning this. In induced electric field, which is non-conservative, this relation will be applicable, integral E dl equal to minus d phi by dt, whereas in conservative field, you know already, integral E dl equal to 0.